All right, in this section, we're going to really expand our rules, our differentiation rules. In section 3.5, we're going to look at derivatives of the trigonometric functions. So the two main trigonometric functions are sine and cosine, and their values are known from the unit circle. Think about it, folks. If you know sine and cosine, you really know everything, because tangent is sine over cosine, and then cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Or you could also say cotangent is cosine over sine. Now, before we determine derivatives for sine x and cosine x, we're going to need to use the definition of the derivative to do that. And before we get to that point, we're going to have to develop two special trigonometric limits. Specifically, the limit as x approaches 0 of sine x over x, and the limit as x approaches 0 of cosine x minus 1 over x. So let's look at the limit as x approaches 0 of sine x over x. You know, the following table and graph can give us a good suggestion for what this limit is. So here's the table. Sure looks like as x is getting close to 0 from the left side of 0, and as x gets close to 0 from the right side of 0, it looks like those functional values are getting close to 1. There's the graph of sine x over x. Supports the table. So the table and graph are both suggesting the limit as x approaches 0 of sine x over x equals 1. Please note that direct substitution wouldn't work in trying to determine this limit. If we try direct substitution, we get the indeterminate form 0 over 0. But folks, at this time, we have to verify what the table and the graph suggests. So to do this, we're going to have to rely on a little bit of geometry and some trigonometry to do this task. So got a figure over here to the right, which is the top half of the unit circle. Recall for the unit circle, r is equal to 1. Now, folks, since r is equal to 1, line segment OA, so let me kind of scroll over that with my mouse here. Line segment OA has a length of 1, and line segment OC, it also has a length of 1. We know angle x, well, it's going to be in radians. Remember from geometry that the area of a triangle is 1/2 base times height. And then remember from trigonometry that the area of a sector of a circle, like a piece of pie or a piece of pizza, is given by area equals 1/2 r squared theta. And again, theta is in radians. So just look at this figure again. Look at triangle OAD. So here's triangle OAD. So the area of that triangle is definitely less than the area of this sector, OAC. And the area of sector OAC is definitely less than the area of triangle OBC. So it allows me to write this compound inequality, that the area of triangle OAD is less than the area of sector OAC, which is less than the area of triangle OBC. Now, folks, I'm calling this compound inequality, I'm giving it a Roman numeral. I'm calling it Roman numeral number 1 because I'm going to reference that here in a little bit. In fact, right now at this time, you know, I have to head off to the chalkboard to continue the derivation of these limits. So let's go to the chalkboard. All right, folks, I just put some stuff up on the board that we saw on the slide. The top half of the unit circle. Remember, x is in radians. The unit circle has a radius of 1, so that means line segment OA is 1, line segment OC is 1, and that we saw on the slide where we left off, the area of triangle OAD is less than the area of sector OAC, and that's less than the area of triangle OBC. And I numbered that compound inequality with a 1. Hey folks, let's look at triangle OAD. Triangle OAD. So I'm saying let's look at this triangle right here, OAD. In triangle OAD, because it's a right triangle, we know from right triangle trig that the sine of angle x is equal to, well, the sine of x is opposite over hypotenuse. So the opposite side is AD and the hypotenuse is OA. But OA, we know OA has a length of 1. So AD over OA is AD over 1. That's just AD. In triangle OAD, the cosine of x. Well, remember right triangle trig. Cosine is adjacent over hypotenuse. So here's x, adjacent over hypotenuse. So it's OD over the hypotenuse OA. But again, OA has a value of 1. So OD over 1 is OD. So, you know what, how about looking at triangle OBC? I mean, we talked about sine, we talked about cosine, we haven't talked about tangent yet. I feel kind of bad for tangent. So in triangle OBC, again, that's a right triangle. Let's write down what the tangent of x is. So remember, right triangle trig, tangent is opposite over adjacent. So it's opposite BC over adjacent OC. But OC is equal to 1, so that simplifies to BC. All right, we're making some progress here. Now let's write down what the area of triangle OAD is. So area of triangle OAD. Well, we reviewed the formula for area of a triangle. It's 1/2 base times height. So for triangle OAD, it's 1/2 the base. The base is OD. So let me put OD in for the base. And the height, well, here's the height of triangle OAD. That's AD. So let me write down AD. Another way to represent this is, look at OD. OD is the cosine of x. Look at AD. AD is the sine of x. So the area of triangle OAD is 1/2 cosine x sine x. The area of, you know, while we're here, let's do the area of triangle OBC. So the area of triangle OBC, we know that's 1/2 base times height. So that's 1/2. So let's look at OBC, the base of triangle OBC. The base is OC. The height is BC. What's the length of OC? It's 1. The length of OC is 1. What is BC? Well, BC is the tangent of x. Alright, feel like I'm making some progress here. The only thing that I have left to do is the area of sector OAC. So the area of sector OAC, we can put that down here. Area of sector OAC. Well, we reviewed the formula for area of a sector. We reviewed that it was 1/2 r squared theta. What's r? I mean, we're on the unit circle, so r would be 1. And theta, well, theta is the angle. Theta is just x, so we get the area of sector OAC to be 1/2 times 1 squared times x. So it's 1/2 x. Since I have an expression for the area of triangle OAD, sector OAC, and triangle OBC, I'm going to substitute these expressions into this compound inequality that we numbered 1. And when I do that, triangle OAD, it has an area of 1/2 cosine x sine x. Sector OAC has an area of 1/2 x. And triangle OBC, it has an area of 1/2 tangent x. I'm going to rewrite tangent. We know tangent is sine over cosine. That way I'll see nothing but sines and cosines in here. So let me just rewrite this compound inequality. Like that, using an old quotient identity. And, you know, I don't like all those fractions in there, so let me just multiply each piece of that, of this compound inequality. I don't know how that happened. Let me just multiply each piece of this compound inequality by 2 to get cosine x sine x is less than x is less than sine x over cosine x. Alright, I'm running out of room, so I'm going to do a little erasing here and pull this compound inequality up here. So hopefully you had that written down in a nice organized manner. Alright, so let me pull this inequality up here. Cosine x sine x less than x less than sine x over cosine x. I'm now going to do something, that this is why I'm going through the derivation. It may not seem obvious to do, but I'm going to divide each piece of this compound inequality by sine x, or multiply it by 1 over sine x, however you prefer to look at it. And when I do that, I get cosine x is less than x over sine x is less than, well, 1 over cosine x. Okay, now I don't know if you remember this from algebra or not, but when you have inequalities like this, you can reciprocate each piece, and if you reciprocate each piece, you have to flip the inequality sign. Again, I don't know if you remember that or not from algebra, but that's what I'm going to do next. So I reciprocate this, so I get 1 over cosine x. I reciprocate the middle piece, and I reciprocate this piece, and then I have to flip those signs. That's what happens when you reciprocate. You have to flip the signs. Now I can rewrite this compound inequality as cosine x less than sine x over x less than 1 over cosine x. And now let's do some limits. The limit as x heads off to 0 of cosine x, this piece here. Direct substitution gives us that limit as 1. The limit as x heads off to 0 of 1 over cosine x. Direct substitution gives us that limit as 1. So we know the limit as x approaches 0 of sine x over x must also equal 1 thanks to the squeeze theorem. When we first learned the squeeze theorem, did I mention how it just keeps popping up in the calc sequence? In any event, we have now kind of mathematically derived or we're given a nice solid mathematical argument to the table and graph that we saw. The table and graph suggested to us that the limit as x approaches 0 of sine x over x equals 1. We now have some mathematical power behind that suggestion. So this is a limit. It's a special trig limit you need to commit to memory. And we're now going to head back to the slides and write down the theorem for this. All right, folks, we've verified or proved, if you will, what the table and the graph suggested about the limit as x approaches 0 of sine x over x. So at this time, I'm going to present a theorem that's going to formalize these two special trigonometric limits. First part, the limit as x approaches 0 of sine x over x equals 1. The second part, the limit as x approaches 0 of cosine x minus 1 over x equals 0. Or we could say the limit as x approaches 0 of 1 minus cosine x over x equals 0. Those are two special trigonometric limits. You need to know these two limits. You need to, commit them to memory. And we're going to actually do an example practice using these two new special trigonometric limits. So, boy, look at this. We have 5 parts in this example. So please write down, get in your notes, this example in all 5 parts. I'm going to head off to the chalkboard to do them. And, I'm probably going to ask you to pause the video and do a couple of them while I'm at the chalkboard. So please get them written down because now I'm heading off to the chalkboard. All right, folks, we saw our theorem with the two special trigonometric limits. And this example, we're going to practice using those two special trigonometric limits. I know the example had 5 parts. I can only get 3 parts on the board right now. So let's try to do part A. Determine the limit as x approaches 0, cosine x tangent x over x. So if you try direct substitution, you would get 0 over 0. So I see tangent x, and I think, let's rewrite that as sine x over cosine x. So then in the numerator, these cosine x's cancel out, and we're just left with sine x over x, which is our special limit that we know is 1. You know what? I would like you to pause the video, and I would like you to try part B and try part C. After you've done that, restart the video, and I'll be here at the board to work through them to make sure you have a correct answer. All right, let's see if you have a correct answer here for part B. Direct substitution gives me 0 over 0. So in the numerator, I can factor out a 3. And now you remember there's an old property or an old law of limits, an old limit theorem that says the limit of a product is the product of the limits. So I could think of this as being the limit as x approaches 0 of 3 times the limit as x approaches 0 of cosine x minus 1 over x. We know the limit of a constant is that constant. This limit, well, that's a special trig limit. We know that limit is 0. So the limit for part B is 0. Hopefully you got that. Part C, direct substitution gives us 0 over 0. So here's how I look at part C. That numerator, sine cubed x, I think of that as being sine x times sine squared x. Then I can look at this product as being sine x over x times sine squared x, that'd be over 1. Then I can use that old limit theorem. The limit of a product is the product of the limits. And this is a special trig limit. We know that's 1. Direct substitution here gives us 0. So this limit, just like part B, it is also 0. So let me do a little erasing here to get parts D and E up on the board. So I hope you got parts B and C there. They weren't too bad. So part D, that was the limit as x approaches 0 of sine 3x over x. And then part E, well, that's the limit as x approaches 0, 3 sine x minus 2 cosine x plus 2 all over x. Okay, part D. Here's the deal with part D. Maybe you know an identity for sine 3x. Maybe you know a triple angle identity. Yeah, I don't. It does exist, but I never bothered to commit it to memory because it is so rarely used. But we want to get the structure. This structure, limit as x approaches 0 of sine x over x is 1. It's the structure that's important. Those have to be the same. Well, right now this says a 3x, that's an x. I need to get a 3 here in the denominator. Then the structure, it'll be the same. Now I can't just put a 3 in there. What I have to do is multiply numerator and denominator by 3 to get the limit as x approaches 0 of 3 sine 3x over 3x. Then I can use that property or that law, that limit law, that says the limit of a product can be rewritten as the product of limits. So it's the limit as x approaches 0 of 3 times the limit as x approaches 0 of sine 3x over 3x. We know this limit, the limit of a constant is the constant. And now we have that structure. Sine 3x over 3x, it's the structure. So this limit is 1, 3 times 1 is 3. Part E. You know what? I'd like you to pause the video and I would like you to try part E. And once you're done with it, restart the video. I'll be here at the chalkboard working through it. Alright folks, here in part E, well, you know, I should mention it, direct substitution would give you 0 over 0. You know, my denominator is a single term. So I'm going to start off by splitting this into a couple of fractions. 3 sine x over x, and then plus negative 2 cosine x plus 2 over x. I mean, it's kind of like the meaning of what a common denominator is. Now I'm going to just do one little rewrite here. I'm going to factor a negative 1 out of the numerator here and turn this addition then into subtraction. Because after I factor out a negative, I'd have plus a negative. That's the same thing as subtraction. So when I factor a -1 out of here, I'll have a 2 cosine x minus 2. You know what? I could do a little more factoring there. I suppose I could have done 2 steps of factoring at once. I could factor a 2 out of the numerator. And then I use a old limit theorem. The limit of a sum or a difference is the sum or difference of limits. So I could rewrite this as the limit as x approaches 0, 3 sine x over x, minus the limit as x approaches 0, 2 cosine x minus 1 over x. I'm running out of room, so I'll just verbalize. This is the limit as x approaches 0 of 3 times the limit as x approaches 0 of sine x over x. Likewise here, I could write it as a product of 2 limits. But we know the limit as x approaches 0 of 3 is 3. The limit as x approaches 0 of sine x over x, that's 1. The limit as x approaches 0 of 2 is 2. Limit as x approaches 0 cosine x minus 1 over x. That's 0. So 3 minus 0. That limit is 3. Part E was kind of cool. In Part E we had both of those special trig limits. Hey folks, let's head back to the slides and see where this is leading us. All right. Now that we have these 2 special trig limits, we are ready to derive the derivatives for sine x and cosine x. In order to derive these derivatives, we have to use the definition of the derivative. And there's also something else we need to remember. We need to remember the sum identities from trigonometry. So remember the cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a times sine of b. And the sine of a plus b equals the sine of a cosine b plus cosine a sine b. So to do this derivation, I am going to head off to the chalkboard and I'm going to pick one of the 2 trig functions, sine x or cosine x. We're going to crank it through the definition of the derivative, and we are going to discover what the derivative happens to be. All right, folks, I decided we are going to determine the derivative for f of x equals cosine x. And I'm going to need to remember that identity over there in doing the derivative. So remember, first we have to use the definition of the derivative. So remember the definition of the derivative. F prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. So that gives us the limit as h approaches 0. Well, f of x plus h is cosine of x plus h. And then f of x is cosine x. And then here's where that trig identity over there comes in handy. Cosine of x plus h. I mean, x is in place of a, h is in place of b, so the cosine of x plus h is cosine x, cosine h, minus sine x, sine h. And then we have a minus cosine x still tagging along. And you know, I'm going to rewrite this numerator because this cosine x wants to get a little closer to this term, which contains a cosine x. So let's just rewrite the numerator as cosine x cosine h minus cosine x minus sine x sine h all over h. And you know, once I do that rewriting, to really make this cosine term happy, I'm going to put these first 2 terms, I'm just going to put them in a group. And then once I put them in a group, I can factor out a cosine x. Leaves me with cosine h minus 1. And here I still have the sine x, sine h. And all of that is over h. So pulling the problem up here, and as I pull the problem up there, I'm going to say, you know, I'm now going to rewrite this as two fractions. I'm going to rewrite it as the fraction cosine x, cosine h minus 1 over h minus sine x, sine h over h. Yeah, I'm starting to see those two special trig limits in here. But let me rewrite this. As the limit as h approaches 0, cosine x times cosine h minus 1 over h minus the limit as h approaches 0, sine x, sine h over h. So folks, remember, it's h is approaching 0. So just like before, when h is approaching 0, we leave the x's alone. So look at this first term. The limit as h approaches 0. Well, the cosine x, we're ignoring it. We have the limit as h approaches 0. These are the terms, that's what involves the h. So the limit as h approaches 0 of cosine h minus 1 over h, that is our special trig limit. We know that limit is 0. So this is cosine x times 0. Limit as h approaches 0 of sine x sine h over h. That's our special trig limit, sine h over h. The limit as h approaches 0 of sine h over h, that's the special trig limit. We know that limit is 1. So we have minus sine x times 1. So cleaning this up, this is 0. So we're left with negative sine x. We have just derived that for the trig function cosine x, the derivative is negative sine x. And we would derive the derivative for sine x in a similar manner. We'd have to use the definition, but we wouldn't be using the cosine a plus b identity. We'd be using the sine of a plus b identity around this step. So we've derived the derivative for cosine x. Derivative of cosine x is negative sine x. Let's head back to the slides and formalize this. Hey folks, at the chalkboard, we used the definition of the derivative to determine that the derivative of f of x equals cosine x is equal to negative sine x. Likewise, we could have used the definition of the derivative to determine that the derivative of sine is cosine. We did derive that the derivative of cosine is negative sine. Folks, I gotta for some reason I have a D in here. Please ignore that D. In fact, in your notes, write cosine of x, not dx. Fat fingers. Folks, these are two derivatives. I mean, you just have to know. You have to know the derivative of sine is cosine, and you have to know the derivative of cosine is negative sine. Let's practice. Let's determine derivatives for the following. So part A, we're going to determine the derivative for f of x equals 3 sine x. Part B, we're going to get the derivative for f of x equals 3x squared sine x. Part C, we'll get the derivative for f of x equals x cubed cosine x. And in part D, we'll get the derivative for the function x squared plus sine x minus x cosine x. And then in part E, we'll differentiate y equals 1 plus cosine x over 1 minus cosine x. So as always, folks, get all of this written in your notes. Chances are I'm going to ask you, when we head off to the chalkboard to do this example, I will ask you to pause the video and do a couple of them on your own. Here I go to the chalkboard. All right, so now we know the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Part A, differentiate f of x equals 3 sine x. So it's the constant multiple rule with our new derivative rule. The derivative of sine x is cosine x. That's it. One step done. Part B, get the derivative of f of x equals 3x squared sine x. Here, we have a product rule here. Your first function is 3x squared. The second function is sine x. So we have to remember the product rule. So the derivative is, using the product rule says the derivative of the first function, 6x, times the second function, plus the first function, times, the derivative of the second function, derivative of sine, is cosine. And that's it for part B. Part C, function is x cubed cosine x. Again, we have a product of two functions. So we have to crank this through the product rule. So the product rule gives us the derivative of the first function, that's 3x squared, times the second function, plus the first function, times the derivative of the second function is negative sine x. And we'd probably, at a minimum, like to rewrite it like that. Okay, there was a part D and a part E. Let me get those written up here. Let's see. So part D, the function was x squared plus sine x minus x cosine x. And then part E, the function was y equals 1 plus cosine x over 1 minus cosine x. And you know what? I'm going to ask you to pause the video, and I would like you to do these two parts. And when you've done them, restart the video, and I'll be here at the board working through them to make sure you have a correct answer. And let me give you a word of warning. Part D. X cosine x is going to require the product rule. But look what is preceding that, x cosine x. It's a minus sign. So I would put the result of the product rule on this x cosine x inside parentheses to make sure I do not make a careless sign mistake. Pause the video, do parts D and part E, restart the video when you're done. Hopefully you'll have the correct answer. All right, folks, let's see how you did on part D here. So I get the derivative to be at 2x. Derivative of sine is cosine x. Minus, this is the product rule. Because it's the product rule, I have two functions, x, cosine x, multiplied together. I'm going to contain the result of the product rule inside parentheses. So the derivative of the first function is 1 times the second function plus the first function times, now the derivative of cosine is negative sine. And then I would clean this up, distribute the negative, so I get negative cosine x or minus cosine x plus x sine x. Because this product would be negative, -1 times that makes it positive. And then it doesn't take too much more to clean it up a little further. I mean, cosine x minus cosine x cancels out. So that looks like a good derivative for part D. Part E. Yeah, we got to use the quotient rule here. So what to call the derivative? Do I want to call it dy dx? Do I want to call it y prime? You make a guess right now what I'm going to call the derivative. I decided to go with dy dx. So here we go. Good old quotient rule. The derivative of the numerator, well, that's a negative sine x. Whoops. Times the denominator minus the numerator times the derivative of the denominator. Well, the derivative of the denominator is negative. Well, that's a negative sine x, but there's a negative in front. So negative. So the derivative of the denominator is positive sine x. All over 1 minus cosine x, that quantity squared. And do we want to simplify this? Let's go ahead and simplify it. Let's distribute a negative sine x here. So we have a negative sine x plus sine x cosine x. And then let's distribute the negative sine. So we'd have a minus sine x minus sine x cosine x all over the denominator squared. And then, well, you know, we did that. We might as well combine any like terms we have. So negative sine x minus sine x, that's a negative 2 sine x. Oh, the sine x cosine x cancel out. Alright, so we did a little bit of simplifying. Alright folks, let's head back to the slides and see what more we can do with the trigonometric functions. In that last example, we noticed that we still need to remember, our old rules of derivatives. We need to remember product rule. We need to remember quotient rule. Continuing on, here's something that's kind of neat. We can make use of basic trigonometric identities. And when I say basic trigonometric identities, I'm talking quotient identities or reciprocal identities, along with our already developed derivative rules, such as the quotient rule, such as the derivative for sine and the derivative for cosine. We can use stuff we already know to determine the derivatives of the remaining 4 trigonometric functions. In other words, we don't have to use the definition of the derivative to determine the derivative rule for tangent x. So I'm going to illustrate this in the following example. We're going to develop derivative rules for the remaining 4 trigonometric functions. So write this in your notes, because I'm going to head off to the chalkboard, and we are going to, we're going to develop derivative rules for tangent x, secant x, cotangent x, and cosecant x. All right, folks, we have 4 more trigonometric functions. We have tangent, secant, cotangent, cosecant, that we need to determine rules for the derivatives of these other 4 trigonometric functions. Now, I could take each one of these 4 and crank it through the definition of the derivative. That would be horrible. The neat thing in mathematics is once I know something to be true, I can then use it going forward. What do I mean by that? I know tangent can be rewritten as sine x over cosine x. I know the derivative of sine, and I know the derivative of cosine, and I know the quotient rule. So I can use the quotient rule. So let's see, the derivative of the numerator is cosine x times the denominator, cosine x, minus the numerator, sine x, times the derivative of the denominator, negative sine x, all over the denominator squared. So we've determined a rule for tangent x, but I think I'd like to simplify this one Well, cosine x times cosine x is cosine squared x. This product would give us a plus sine squared x. And I could go a little bit further. We know a trig identity. Think it was a Pythagorean identity. Cosine squared x plus sine squared x, that's 1. So this looks like it would be a lot better to remember for the derivative of tangent x than this, but I could simplify that even more. We know 1 over cosine. 1 over cosine is secant. So 1 over cosine squared is secant squared x. And that's what we need to know. For tangent x, the derivative of tangent x is secant squared x. Well, let's see what we can do in part B. The function is secant x. Well, maybe a place for me to start here is to rewrite secant as 1 over cosine. Just use a reciprocal identity. Now I know the quotient rule. So why don't I crank this through the quotient rule? The derivative is the derivative of the numerator, so that's 0 times cosine x, minus the numerator 1, times the derivative of the denominator, well, the derivative of the denominator is negative sine, all over the denominator squared. Yes, we're going to clean this up. This is 0 minus a negative. Gives us a positive sine x over cosine squared x. But I'm going to go further because sine x over cosine squared x, I can think of that as sine x over cosine x times a 1 over cosine x. Well, what's 1 over cosine x? That's secant x. What's sine over cosine? That's tangent. This is the rule for the derivative of secant. The derivative of secant is secant x tangent x. So look, we have derived 2. There's 2 to go. And you know what I would like you to do? I would like you to pause the video, and I would like you to do parts C and D to come up with the rules for the derivative of cotangent and the derivative of cosecant. And once you've done that, restart the video. I'll be working through them on the board to make sure that you are correct. Alright, let's see how you did here. Part C, coming up with a formula or a rule for the derivative of cotangent. I would rewrite cotangent using a quotient identity as cosine x over sine x. Then I would crank this through the quotient rule. So the derivative of the numerator is negative sine x times the denominator minus the numerator times the derivative of the denominator. The derivative of sine is cosine, all over the denominator squared. So cleaning it up, this will be a negative sine squared x minus a cosine squared x over a sine squared x. So in the numerator here, I'd factor out a negative 1. And when I do that, I see an old familiar Pythagorean identity. Sine squared x plus cosine squared x is 1. So this leaves us with a negative 1 over sine squared x, which is, well, 1 over sine is cosecant, so 1 over sine squared is cosecant squared. But don't forget the negative sign. Negative cosecant squared x. So the derivative of cotangent is negative cosecant squared. Part D, well, I would rewrite cosecant as 1 over sine and then crank this through the quotient rule. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. So cleaning that up, we have negative cosine x over sine squared x. I can think of that as being negative cosine x over sine x times a 1 over sine x. So 1 over sine is cosecant. Cosine over sine is cotangent. Don't forget the negative. So negative cosecant x, cotangent x. So there you have it. We have now derived, we now know the formula. We know the rule for all 6 trig functions. So let's head back to the slides because I'm going to put this into a theorem, kind of formalize it a little bit. So let's go back to the slides. All right, as we saw in that last example, we could use information we already knew to come up with derivative rules for the remaining 4 trigonometric functions. That's what's kind of cool here in mathematics. You can use something that you already know to extend your knowledge base. And at this time, we have determined derivatives for all 6 trigonometric functions. We saw we didn't need to use the definition of the derivative for the final 4 trig functions. We just simply used information we already knew. And so here's the theorem. This is the derivative of all 6 trigonometric functions that you should know all 6 of them. So the derivative of sine is cosine x. The derivative of cosine x is negative sine x. We developed that the derivative of tangent x is secant squared x. The derivative of cosecant x is negative cosecant x cotangent x. The derivative of secant x is secant x tangent x. And the derivative of cotangent x is negative cosecant squared x. All right, folks, I kind of came up with a little trick many years ago to help me remember these. And it utilizes our knowledge of cofunctions from trigonometry. We just need to remember which functions are cofunctions. Tangent and cotangent. They are cofunctions. Secant and cosecant. They are cofunctions. So I committed to memory here that the derivative of tangent x is secant squared x. That told me, that gave me for free that the derivative of cotangent x, it's the cofunction of tangent, equals the cofunction of secant squared. Negative cosecant squared x. I just had to remember that there would be a negative sign. Tangent has a cofunction of cotangent, so the derivatives are cofunctions. But remember the negative sign. I committed to memory that the derivative of secant x is secant x tangent x. That gave me for free that the derivative of the cotangent, or the derivative of the cofunction, the derivative of cosecant, is just cofunctions. I had to remember the negative sign. In any event, whatever it takes, you have to know these 6 derivatives. So let's practice these, all these derivative rules now. And so in this example, we're going to differentiate in part A, y equals secant x cosecant x. And in part B, we're going to differentiate y equals tangent x over 1 plus secant x. So get this written in your notes because I'm heading off to the chalkboard to work through them. All right, now we know the derivatives for all 6 trig functions. In this example, we were asked to differentiate in part A, y equals secant x plus cosecant x. So what to call the derivative? Y prime or dy dx? I think this time I'll call it y prime. All right, the derivative of secant x is secant x tangent x plus, now the derivative of cosecant, I'm going to go over this cofunction trick again. The derivative of cosecant, it has the same structure as the derivative of secant, except it's cosecant cotangent. And then I have to remember there's a negative sign in front. So the derivative of cosecant is negative cosecant, cotangent, which I would write the final derivative like this. Part B, y equals tangent x over 1 plus secant x. So we're going to have to use the quotient rule here. And you know what? I'm going to call this derivative dy dx. So here we go with the quotient rule. So the derivative of the numerator, the derivative of tangent, is secant squared times the denominator minus the numerator times the derivative of the denominator. Well, the derivative of secant x is secant x tangent x. And then all of that is over the denominator squared. You know, let's clean this up a little. Let's distribute the secant squared. So we get a secant squared x plus a secant cubed x. Here, after distribution or multiplying, we get negative secant x tangent squared x. This chalk. You know what, in the numerator, I guess in the numerator, you know, I could factor out a secant x. So let's do that. And that leaves me with a secant x plus a secant squared x minus a tangent squared x. Something looks awfully familiar here with the secant squared x minus tangent squared x. I mean, I guess I'm remembering, you know, as an aside, I'm remembering a Pythagorean identity that says 1 plus tangent squared x is equal to secant squared x. So that, from this identity, 1 is equal to secant squared x minus a tangent squared x. So this secant squared x minus tangent squared x, I can replace it with 1. Well, now I'm getting somewhere. And then, oh, check this out. This secant x plus 1, it's a factor in the numerator, and it's a factor in the denominator, so I could do a little canceling to get secant x over a 1 plus secant x. And that's as far as I'm going to go because, well, I'm out of room. But it was just fun to review some trig identities in there. So here's what I'd like you to do right now. Just get a little bit of practice with all of the derivative rules here. In the section 3.5 exercises, I would like you to pause the video, go into the section 3.5 exercises, do numbers 42 and 44, and then you know the drill. Once you're done, restart the video, and I'll be here at the board working through them to make sure you have correct answers. All right, number 42, you were asked to differentiate y equals tangent x plus cotangent x. Let's see, should I call the derivative y prime or dy dx? We know it doesn't matter. I'll call it dy dx. All right, derivative of tangent, that's secant squared. The derivative of cotangent is negative cosecant squared. And that's it. That's the derivative. 44, here I'll call the derivative y prime. So, oh boy, we have the product rule here. We have two functions. Secant x is the first function. Tangent x is the second function. So, cranking it through the product rule, the derivative of the first function, secant x, well, that derivative is secant x tangent x times the second function, tangent x, plus the first function, secant x, times the derivative of the second function. So the derivative of tangent x is secant squared x. And, you know, I guess I could write that as a secant x tangent squared x plus a secant cubed x. I mean, and if you know, we could factor out a secant x. And I'm not going to go any further. So folks, that's it here for section 3.5. We had a lot. It was like a trigonometric intensive section. You know, in this section we learned 2 new special trigonometric limits and the derivatives of the 6 trigonometric functions. So at this time, why don't you head off, do the exercises in section 3.5, and thanks for watching.